Let's talk about how to determine whether or not two triangles are congruent. In our previous video, we discussed that triangles are congruent if all three of their pairs of sides are congruent and all three of their pairs of angles are congruent. And that's a lot of information to have to prove in order to show that triangles are congruent. The good news is we have some shortcuts. Instead of proving all three pairs of angles and all three pairs of sides are congruent, you could use one of the following 5 theorems instead. First, we have SSS, which is short for the side-side-side triangle congruence theorem. And it states that if you can show that all three pairs of sides are congruent, that's enough to say that the triangles are congruent. You don't actually have to know anything about the angles at all. We also have the side-angle-side triangle congruence theorem, or SAS. And it states that if you have two pairs of congruent sides, and the included angles are also congruent, then the two triangles are congruent. It's important to note that the angles have to be included between the two sides. And that means like what you see on these two diagrams. Angle B is included between the two sides that are marked as congruent. The two sides that are marked as congruent create angle B. Likewise, these two sides that are marked as congruent in triangle DEF, those two sides create angle E. Those are called the included angles, and those are the ones that have to be congruent in order for the two triangles to be able to be proved congruent. If you knew the two sides that were given are congruent and angle A was congruent to angle D, or that angle C was congruent to angle F, unfortunately that's not the right kind of information because those angles are not included between the two congruent sides. We also have angle-side-angle triangle congruence theorem, or ASA, and that is kind of the same thing as SAS, except backwards. Instead of having two congruent sides and one congruent angle, we have two congruent angles and one congruent side. Again, the side has to be included between the two congruent angles. So if I know that these two angles are congruent to two angles in the other triangle, I have to have side AB as the congruent side, not BC and not AC, because these aren't included between those two angles. Side AB is the side that connects the two congruent angles. So this would be an example of angle-side-angle, where I have two pairs of angles that are congruent and their included sides are congruent. That would be enough information to say that the two triangles are congruent. However, we also have angle-angle-side, or AAS. So for this theorem, you could have a non-included side. So if I have the same two angles that we talked about on the previous theorem, but this time one of the other sides, not the one that connects the two congruent angles, but one of the other two, that would also be enough information to say that the triangles are congruent. And then finally we have one that's a little bit different than the others, and that's because it's specific to right triangles. The HL, or hypotenuse leg triangle congruence theorem, only applies if you have a right triangle. It says that if you have two right triangles and their hypotenuses are congruent, the hypotenuse is the side that's across from the right angle, it's always the longest side in a right triangle, and one of the pairs of legs are congruent. So H is hypotenuse, L is leg. If I have that situation, then those two triangles must be congruent as well. So the only things that we're missing here are angle, 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 and side, side, angle. Those are the only combinations of A's and S's that we didn't use, and that's because those two things are not triangle congruence theorems. Knowing that all three pairs of angles are congruent is not enough information to say that the two triangles are congruent. For example, what you see on the screen right now are two different triangles that both have the same angle measures. We actually call that a dilation, and we'll learn a lot more about that in a future chapter, but knowing that the angles are congruent but nothing about the sides does not tell us that the triangles are congruent. Additionally, you can't use side-side angle, which would be two sides are congruent and their non-included angles are congruent, like what you see on the screen now. Those two triangles have two pairs of congruent sides and one pair of congruent angles, but since the angles aren't included between those two congruent sides, as you can see, it makes different triangles. An easy way to remember that this doesn't work is that if you spell SSA backwards, it makes a cuss word. And we can't cuss in geometry class, so angle, 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 and cuss words are not allowed. So the things you can use to prove that two triangles are congruent is SSS, SAS, ASA, AAS, and HL. You cannot use AAA or ASS. So let's try a few examples. we're going to look at the information that's been provided on these diagrams and determine whether or not the triangles are congruent. If they are, then we'll state which theorem we would use, and we'll write a congruent statement. Looking at these two triangles, I see that they have two pairs of congruent sides, and they have one pair of congruent angles, and the congruent angles are included between those two congruent sides. So yes, indeed, these two triangles are congruent to each other because of the side-angle-side congruence theorem. We have a side, and an angle, and a side, and therefore the triangles are congruent. So now let's write a congruent statement. Remember that you can name a triangle by stating all three vertices of that triangle in any order that you want to. So let's say, for example, I call the first triangle WHB. Well, I can't just call the other triangle in whatever order I want to then. I have to make it in a corresponding order. So the first triangle's name, make it whatever you want. But the second triangle's name has to go in a corresponding order in order for your congruent statement to be correct. So if I start out with triangle WHB for the first triangle's name, I would need to call the second triangle GVP. That way it goes in a corresponding order. W is the angle that is across from the single marked side, H is the angle that's across from the double marked side, and B is the angle that's marked with one congruence mark. So I have to go in the same order when I name the yellow triangle. So I went single, double, single. So across from the single mark is G, across from the double mark is V, and the single angle mark is P. So I have to call it GVP. Let's try another one. These two triangles have three pairs of congruent sides, and that matches to the side-side-side triangle congruence theorem. These two triangles have to be congruent. So if I call my first triangle DZJ, well, D is across from the single mark, Z is across from the double mark, and J is across from the triple mark. So if I call that first triangle DZJ, I have to call the other one QCY. Q is across from the single mark, C is across from the double mark, and Y is across from the triple mark. That way it goes in the same order as what I called my first triangle. How about our next example? I see two pairs of corresponding sides that are congruent and one pair of corresponding angles that are congruent. So is this like the first example that we saw? Is this side angle side? Well, not quite, because the angle is not included between those two congruent sides this time. The angle that we know is congruent is not included, which means I can't prove that these two triangles are congruent. Maybe they are, maybe they're not. There's just no way to tell. It's not the right kind of information to use a triangle congruence theorem. It would actually be the ASS triangle congruence theorem, and as we discussed, we can't cuss in geometry class, so that wouldn't work. These two triangles cannot be proven congruent. Our next pair of triangles, I see two pairs of congruent angles and one pair of congruent sides, and the pair of congruent sides is not included in between the two angles. It's a different side. So that would be the angle, angle, side triangle congruence theorem. Angle, angle, side. So if I call my first triangle KSX, so that's the single arc, no arc, and double arc. Single, no, double. I have to go in the same order when I name the other triangle. So single, no, double. UBT would have to be the name of that triangle. Let's talk about our next example. I see two congruent angles and one congruent side, but then I see two congruent sides and one congruent angle. So the green triangle looked like an angle-side-angle situation, but the yellow triangle looks like a side-angle-side situation. These can't be proven congruent. I don't know the right kind of information here in order to prove that these two triangles are congruent. There's just no way to know, based on the information that's been provided on these diagrams, whether they're congruent or not. Our next two triangles are a little bit unique compared to the other ones we've seen because they're right triangles. They both have a right angle. Angle D has a little square at the vertex, and angle S has a little square at the vertex, so these two triangles are both right triangles. And I see that these two right triangles have their hypotenuses marked as congruent, and that they have one pair of legs marked as congruent. So I can use the HL triangle congruence theorem to say that these two triangles must be congruent. If I call my first triangle VDL, which again, you can name it whatever you want to. This first triangle, you can write its name in whatever order you want to, but you have to make sure that the second triangle's name goes in a corresponding order. So if I call this VDL, V is across from the double, D is the right angle, and L is the one that's across from the side that's not labeled as congruent. So double, right angle, nothing. So I have to call the other triangle in the same order. Across from the double, right angle, across from nothing. So that has to be PSW. So triangle VDL is congruent to triangle PSW. On our next diagram, I see 3 pairs of corresponding angles are marked as congruent. However, that's not the right kind of information in order to show that the triangles are congruent to each other. These cannot be proven congruent. We'll learn in a future chapter that they can be proven to be similar, but for this chapter we're focusing on congruent polygons, and this is not enough information to prove that. Both of the triangles in our next diagram have 2 pairs of congruent angles and 1 pair of congruent sides, and that congruent side is included between the 2 angles that are marked as congruent. That would be an angle-side-angle situation. So if I call my first triangle K and Q, so that's no marks, 1 mark, 2 marks, I have to go in the same order for my second triangle. So no marks, 1 mark, 2 mark, I have to go no marks, 1 mark, 2 mark, so I call that GTJ. Everything that we've looked at so far has been 2 triangles that aren't connected in any way, but it's actually fairly uncommon to see triangles that look like that. It's way more common to see 2 triangles that share something or are connected in some way, like what you see in this diagram. Can we prove that the green triangle and the yellow triangle are congruent to each other this time? Well, yeah, they each have 2 congruent angles and 1 congruent side, and the congruent side is included between those 2 congruent angles, so this would be angle-side-angle. If I call the green triangle ADC, so that's 1 angle mark, no angle marks, 2 angle marks, ADC, that would correspond to, let's see, 1 angle mark, no angle marks, 2 angle marks, so that would have to be CBA. These 2 triangles would have to be congruent to each other because of the angle-side-angle triangle congruence theorem. What about these 2? Well, I see right triangles again. They both have a right angle, and I see that they share this leg. Those legs have to be congruent to each other, and they also have their hypotenuses are marked as congruent. So I could use HL to say that these 2 triangles are congruent. If I call the first triangle ABD, A is the angle that is across from the single mark side, B is the right angle, and D is the angle that's across from the no marking side. So 1 marking across, right angle, no markings across. I have to go in the same order to name the other triangle. So across from the 1 marking, the right angle, and then across from no markings, that would have to be triangle CBD. In our next triangles, we see 3 pairs of corresponding angles that are congruent, but again, angle, angle, angle is not a triangle congruence theorem, it is a triangle similarity theorem. So for now, all we can say is that these 2 triangles cannot be proven congruent. For our next triangles, I see 3 pairs of congruent sides, and therefore I could use side, side, side to say that these 2 triangles are congruent to each other. If I call the first triangle triangle ABD, well, A is across from the single marking, B is across from the triple marking, and D is across from the double marking. So I went single, triple, double. So I have to do the same thing on the other side, across from single, across from triple, and across from double. So I could say that triangle ABD is congruent to triangle CBD. On our next diagram, there is not yet enough information to say that these 2 triangles are congruent to each other. I have 1 pair of congruent angles and 1 pair of congruent sides. Knowing 2 pairs of things are congruent is just not enough information to say the triangles are congruent. So my question to you is, what extra information would you need to know in order to say that these 2 triangles were congruent to each other? Because right now it's not enough information, it's just an angle and a side. What other pair of congruent things would you need to know in order to say that these 2 triangles are congruent? Well, you actually have a few different options. If you knew that angle C was congruent to angle F, then we could use angle side angle. If this angle was congruent to this angle, then I would have an angle and a side and an angle. The side is included between the 2 angles, so I could say the triangles were congruent using ASA. Or you could have picked the other pair of angles. If I had said that angle B was congruent to angle D, I would have an angle and a side. The side is not included between the two congruent angles, so I would use angle, angle, side. Or if you knew that side BA was congruent to side DE, we could use side, angle, side, because I would have two pairs of congruent sides, and the congruent angle is included between those two sides, so I could use side, angle, side. And that's the basics of what you need to know about determining whether or not two triangles are congruent. In the next part of this lesson, we're going to actually write two-column proofs to show that two triangles are congruent to each other.